Welcome back to Module 1. I hope you've enjoyed Professor Van Diggelen and my take about why GPS is so important and a little bit on how it works. Today, I'd like to dig into snippet 1.4, where we'll really talk about the organization and goals of the course. So specifically, course objectives. We'll introduce the smartphone-based experiments that we've designed for you and give you a little bit of a feeling for how they should work. And then finally, we'll talk about the prerequisites for taking this course. So what I'll do there is foreshadow some of the more technical topics that we're going to talk about, and you can judge whether or not you're well prepared for that or prepared to do the study required to bring yourself up to speed. Here are the course objectives, and I list them in a slightly unusual way. I list them based on how does GPS work, and the list there is pseudoranges, clocks, orbits, spread spectrum signals, microelectronics, and so-called indoors and instant or assisted GPS. And these are topics that we'll cover, and they're also the list of the real innovations that GPS required. They are the big steps that took GPS from a rather raw concept in the 1970s through to a system that's used today by over 3 billion people. And you can see the list is long. Pseudoranges, this speaks to this point that I made a couple of snippets ago, that the measurements are used not only to solve for user location, but also the user clock offset. That was an important step in terms of how GPS works. It meant that the clocks in the ground equipment and the user equipment could be inexpensive. And if that were not true, if the designers had not chosen pseudo-range measurements, then the widespread use of GPS never would have happened because the user clocks would have been too expensive. On the subject of clocks, they're remarkable both on the user side, based on what we were just talking about, but also in space. No one had deployed atomic clocks in the Van Allen belts before GPS. So that was another big step forward in terms of the technology that was required. Orbits, we'll take a historical view. We'll talk about the work, the Renaissance work of Tycho Brahe, Johannes Kepler, and Isaac Newton as they put together the basic ideas that GPS implements and uses every day in every single user receiver. We'll talk about the spread spectrum signals, carefully crafted signals that enable the user equipment to measure the arrival time of the signal to within about 1 billionth of a second, or 1 nanosecond. Microelectronics, we won't address that explicitly, but clearly the Moore's law has benefited GPS enormously. The cost of a processor and the cost of the other integrated circuits required to implement GPS has dropped dramatically from the 1970s, where the first GPS receivers cost on the order of $200,000, through to today, where a smartphone includes a GPS receiver, which cost about $1. And then another big emphasis will be indoors and instant. This is so-called assisted GPS, and Professor Van Diggelen is a master of that field, and so we're fortunate that he will guide us through it. So that's the technology, how does GPS work, part of our course. The other part that we're eager to include and eager to expose you to is why do we do it? What does it do for us? And in that case, there's not much else we can do other than pick our favorite examples, because the breadth is so great that my real wish is that you go out and explore it, use the internet, use whatever materials are at hand to get a feeling for the breadth of GPS applications. It expands every day. It's really remarkable. Here are phone-based experiments depicted, and we are going to hope that many of you will participate in this. you do not all have to. We are going to make the Statement of Achievement available to the people who do the quizzes but don't do the phone-based experiments. But if you do go ahead and include the work on the phone-based experiments, it will be a Statement of Achievement with distinction. So please be aware of that. One constraint that's very important is that the apps that will ask you to download and use to come up with displays like what you see there do not work on Apple products. So this aspect of the course is really enabled by Android. So hopefully you have an Android-enabled GPS device, be it a phone or whatever. If you only have an Apple device, then you will have to go out and borrow, hopefully, from a friend, their Android-based phone. In terms of prerequisites, let me put this slightly frightening view graph there. These are the so-called navigation equations of GPS. And at the top, the tau that you see there is the same pseudo-range equation that I showed a couple of snippets ago. It's rewritten using more vector format, and hopefully you're comfortable with that. And when we stack together, let's say 10 or so GPS measurements, we get that system of equations shown in matrix form down at the bottom. So to really appreciate this course, you'll have to have that kind of familiarity with linear algebra. Don't worry, we'll go through this development carefully when we get there, but I want to foreshadow for you the kind of things that we'll be looking at in this course. In addition, we'll expect and need some kind of feeling for probability. And what you see there sketched in my hand is a probability density function, and that is used to describe the errors in the system. It's used to describe both the errors in the pseudo-range measurements, they're invariably there, and those errors propagate through to becoming errors in our estimates of x, y, and z. And so that whole language is cast in the language of probability. So I hope that you have some familiarity with that. If not, please be prepared to do some study outside of the MOOC itself. Finally, here's a sketch of a single GPS orbit. I'll make it clear for you. Here's the satellite. Here's the orbit rising here above the equatorial plane and going down there. Here's the Earth center right here in the middle. And as you can see, there are a lot of parameters associated with specifying where the satellite is relative to the Earth. And some of those parameters are devoted to describing the shape of that green orbit. Some of those parameters are devoted to describing how that orbit sits relative to the mass center of the Earth. And then finally, one last parameter is devoted to describing where the satellite is in that orbit, thus described. So GPS is a subject, and this course is devoted to drawings and pictures of how a given scenario looks. Where's the satellite relative to the user? Where's the satellite relative to the reference station used in differential GPS? So I hope and wish that you have that kind of familiarity with geometry. So please think about that, the linear algebra prereq, the probability knowledge that we're hoping for, and then just the familiarity and comfort with this kind of geometry is also something that we want in terms of a prerequisite. So that's it for this snippet. When we come back, we'll take up snippet 1.5 or topic 1.5, which will be more about the course schedule and the logistics. Thank you very much.